You look at the periodic table. In the periodic table, what's similar to oxygen but is heavier than oxygen?
Sulfur.
Sulfur, yeah. Sulfur, selenium, tellurium, all those are heavier. And so this is simple. Try to replace the oxygen with sulfur instead. And so that's what I was doing on there. And that changes where it starts to vibrate. It's heavier, it starts to vibrate at different energies. And then hopefully open the window. And so it's more transparent infrared radiation. Microwaves, on the other hand, microwaves don't have enough energy. Microwaves are a little bit lower in energy. They don't have enough energy to cause them to vibrate. You know what microwaves do?
They vibrate water molecules.
Well, they don't actually vibrate. They can, they do something else. Do you know about motion?
I just said they resonate with frequency.
They resonate, but they can resonate by vibration. But what other ways do we have motion? Do you know the 3 types of motion?
Oh, transitional, rotational.
Yeah, translational motion just means going from one point in space to another. What else? Vibrational means the atoms are vibrating like this. When do the atoms stop vibrating? The atoms are always vibrating, right? If it gets hotter, they're vibrating more. If it's colder, they're vibrating less. But those vibrations actually can stop at where? At 0 Kelvin, and we call that temperature absolute 0. Because once they stop vibrating, then there's no more. Actually, you'd think there's no more energy because they stopped. So there's no more kinetic energy. We have 2 types of energy: kinetic energy, which is the energy of motion, and what's the other type of energy? Potential energy, which we'll talk about later. Are you registered in the class?
Yeah, I went to the wrong room.
Okay.
Sorry.
I thought we were doing good, but now maybe we're still all right. If you're trying to add the class, which is only one, is there only one person trying to add the 2? If you're trying to add the class, I'll have to see. If there's some no-shows that are showing up tomorrow or this week. But there's translational, there's vibrational, and what's the other kind of motion? Rotational motion. And so what microwaves do is they're tuned to the frequency that rotates water molecules, that causes motion. And so anyway, so this is just some review, I think, or some conceptual review stuff. It's all the same stuff, and in fact, that's what we're going to be dealing with in this semester. A lot of the same stuff you had in Chem 4, but hopefully more depth than we covered in Chem 4. Some of it will be new, though, probably completely new. And so I was working on that, and in the materials research lab, they were working on lots of different things. I remember there's one professor there who was putting yeast cells into this instrument. This instrument measured the yeast metabolism. And then what he did was he bombarded the yeast cells with gamma radiation. Gamma radiation, what is that? Is that electromagnetic radiation or is that particle radiation? Do you guys know the difference between electromagnetic and particle radiation? Can you give me an example of each, of both?
There's particle radiation, alpha, beta.
Yeah, alpha and beta particles. Alpha particles are they often are described as the nucleus of a helium atom because they consist of 2 protons and 2 neutrons. And there was a very famous experiment by who's that? Very famous experiment where they bombarded.
The Manhattan Project?
Not the Manhattan. This predates the Manhattan Project by like a couple of centuries.
It wasn't the experiment where they bombarded a piece of gold foil
with alpha particles. Alpha particles are our particle radiation. So they put a radioactive source. This radioactive source had big nucleus, which was radioactive, unstable, and chunks of it broke off. It's too big to hold together. Those chunks are alpha particles, and then they put a little pinhole there, so the alpha particles shot through, and then bombarded the gold foil. And then what was the end result of that experiment? Did the alpha particles punch holes through the gold?
No, they bounced around.
Yeah, so that experiment was pretty critical for determining what model of the atom was correct. What was that model? The Bohr? No, that's not quite. Bohr came later. And actually, Bohr, unfortunately, was... is the Bohr model still in use today? They're teaching it, but is it still in use? No. I mean, the Bohr model has been abandoned, unfortunately. But it's still useful to know. Somebody? The what?
Lewis structure.
Not the Lewis structure.
No, just notation.
Uh-huh.
The majority of
Yeah, that's it pretty much. It's the nuclear atom model versus the plum pudding model. That was a big experiment for that. That was one of the big uses for particle radiation back in the day. Alpha particles are quite dangerous, though. Alpha particles are quite dangerous because one, they're gas, and two, are alpha particles radioactive themselves? Alpha particles come from a radioactive atom. A radioactive atom, this thing's unstable. It's got an unstable nucleus. Chunks of it break off. These chunks are alpha particles. Are the alpha particles themselves radioactive? That is, are they unstable and then they disintegrate in some way? No, alpha particles aren't. The alpha particles, and this is what we need. Chemists are most interested in, well, actually, we want to know what it's made of. So alpha particles, helium, we call it helium because it's got 2 protons and then 2 neutrons. So how would I show 2 neutrons on this? This is a nuclear symbol for helium. I would write what number up here to indicate that it has 2 neutrons. This would be 4. That tells me that's 2 protons and 2 neutrons. Does an alpha particle have any electrons? No, an alpha particle has no electrons. Nuclear chemists don't care about the charge. And so oftentimes you'll see an alpha particle written without the charge, but chemists care a lot about the charge. And the charge of an alpha particle, if it has no electrons, what's the charge of an alpha particle? Positive 2. Yeah. So I'll just write it 2 plus. And so that would be an alpha particle there. And so how big is a nucleus compared to an atom, roughly? If an atom's this big, how big is the nucleus? Roughly. This big? If an atom's this big, the nucleus is this big? This big? I mean, if an atom's this big, maybe this big? What do you think? A softball? So a softball would be the nucleus, the basketball would be the atom?
Yeah.
Okay, anybody else?
It depends.
It depends.
How many electrons?
Yeah. Let's say there are, it's going to depend on how many electrons. That's true. But the scale, I'll just get it close enough to order of magnitude, maybe. Let's say there's 1 electron, hydrogen atom. So if a hydrogen atom is this big, how big is the nucleus? Just 1 electron is a hydrogen atom. Are you registered in the class? All right, now we're over. Booked, so I'll have to figure out. just approximately. You know, the reason I'm asking is you need to, you know, it's a good idea to have some stuff. I mean, this class isn't all memorization, but you need to have some stuff memorized. You know, um, especially with things with scale. You know, some people will say, "Oh, that's just a little bit of energy." Well, you know, people are going to question you about what is a little bit. So if I said I had 10 to the minus 19 joules, is that a little bit of energy? Or 10 to the minus 18 joules? 10 to the minus 18 joules, it's got to be a little bit of energy. But, I mean, how warm will a cup of coffee get if you have 10 to the minus 18 joules of heat applied to that cup of coffee? Would you expect any change in temperature? No, you wouldn't expect any change. I mean, you guys know that you may or may not have memorized. Do you know what the heat capacity of the specific heat of water is?
1,000.
Well, some people have. It's an easy number to remember because it's the definition of the calorie. What is the definition of the calorie?
I don't know the definition of calorie, but isn't it like 4,160 joules per kilogram of water?
Kinda. But
Yeah, I learned it in 1B, so or physics 1B.
physics 1B. Okay, maybe are they talking about some other units then? Maybe we gotta watch out for the units, especially when you talk to physicists. Because physicists often use different units than chemists. But does anybody remember the definition of the calorie? .184 joules per gram degree C. That's the definition in that's the specific heat of water. 4.18 joules. 4.18 joules will heat up a gram of water by degree C. And the calorie, you know what the calorie is? 1 calorie is equivalent to how many joules? Here, I'll be right back. Let me grab a chair.